Okay, so let's start by considering this example here, which is probably the most simple example we can imagine in perturbation methods, and which is definitely an example by which we should start to understand what we mean by perturbation techniques. So we want to solve that equation, which is quadratic equation in X, very simple. We assume that epsilon is a small number here. Epsilon is much smaller than 1, could also be positive. And we are interested in the determination of X, possibly as a function of epsilon, the perturbation we have added. Okay, why is it a very good problem to start with? Because we can cheat, and well, I don't know whether this is really cheating or not, but we can definitely write the exact solution of this problem. Exact solution, and the exact solution to that problem is something we can easily get just using the rule of the discriminant. So 1/2 minus b, so this is minus epsilon, plus or minus 1/2 again here, and square root of b squared minus 4ac, which reads like this. So it means this is minus epsilon over 2 plus or minus square root 1 plus epsilon squared over 4. So if you remember that the square root of 1 plus, let's say p, when p is a small number, is 1 plus p over 2 plus things that are of order p squared, then in fact we have x is equal to minus epsilon over 2 plus or minus 1 plus epsilon squared over 8, and plus things that are of order 4, which means that we have two roots, x1 and 2, that are equal to plus or minus 1, okay, coming from here, minus epsilon over 2, and plus or minus epsilon squared over 8, plus some additional terms, which I have neglected. Okay, cool. So you would wonder why I developed this asymptotic sequence. And well, we understand in a few minutes that what we need to do, or what we want to do in a perturbation approach, is to aim for exactly that asymptotic sequence. Okay, so this is the objective that we would like to reach. Okay, so maybe just to start with this problem, for which we have an exact solution, we could also try to have a look at the problem by means of a graphical representation, right? And so if we plot just x squared minus 1, this is a function here that has two roots, plus 1, minus 1, and which looks like this. All right, and then that's x squared minus 1. Then if I want to add epsilon times x, which is something like this, epsilon x, then it means, it means that the point here in the middle is not shifted up. Everything on the right is shifted up. Everything on the left is shifted to the bottom. All right, so it means that the curve that we obtain is something like this. Okay, this is a little bit exaggerated. And on the other side, we have something like that. And so what do we see? We see that the root that was initially located here at 1 is shifted to the left by a certain quantity. The one that was located here at -1 is also shifted to the left by a certain quantity. And the question, of course, that we are interested, we are interested to solve is how much. And we see that we answered already quite well with just by looking at the exact solution, because we see that the solution of the problem is ±1 minus epsilon over 2. So it means that if we decided to truncate the sequence after the first correction, so dropping terms in epsilon square, it means that we will go to the left by a quantity equal to epsilon over 2. Problem solved, right? The thing is that later, we won't have the chance to be able to write the exact solution and to derive the series expansion of the exact solution in order to get the asymptotic expansion of the solution. So we would like to determine whether or not there is a method to determine this shift, so minus epsilon over 2. We would like to see whether or not it could be possible to derive this expression or obtain this expression without having to write the exact solution of the problem. All right, and so for this, we can use a method that is called the expansion method. All right, expansion method. So before talking about expansion method, we said whoever talks about perturbed problem needs to first recognize there is an unperturbed problem. And it is important to make sure that the unperturbed problem is something you can solve, because if you can't solve the unperturbed problem, there's no chance you'll be able to apply a perturbation technique. All right, so the unperturbed problem is the one we get, I repeat, when epsilon is equal to 0. And this problem is x squared minus 1 is equal to 0, which means that the solution of the unperturbed problem, in this case, this is plus or minus 1. Okay, easy game. That's something we already got. Okay, and now let's see how the expansion method works. The expansion method works by assuming that the solution, assume the solution of the problem can be written in the form of what is called an ansatz. Ansatz. I think this is a German word which means supposed form or supposed shape. And in this case, we're going to assume that x is equal to x0 plus epsilon x1, epsilon square x2, and so on. Okay, be ready to write this, because that's something we write permanently in a course on perturbation techniques. And so then what do we do with this? We substitute this ansatz in the governing equation and see what we obtained. Okay, so then substitute in governing equation. Then we end up with x squared, which is x0 plus epsilon x1. I use 3 little dots notation here to make it easy. This is not really formal. We see a little bit later how we can write to make it look more neat and make sure if you want to use those techniques in your publications, you end up with notations that are similar to what standards are. All right, so what I basically did here is I started again from the governing equation, x squared plus epsilon x minus 1. Okay, let's expand. So if we expand the first term, we have x0 squared plus first double product plus, times epsilon plus second double product, which is twice x0, x2 epsilon squared, then plus here the second squared term, and then the following terms will be things of order epsilons to the third, plus epsilon x0 plus, sorry, I should write first like this, minus 1 is equal to 0. Or I should write 0 plus things of order epsilon to the third, and I collect in this term, in this extra symbolic term, everything that I've just discarded. And so let's just maybe rewrite this and sort out the equation at the different terms. So we have x0 squared minus 1 plus epsilon multiplied by twice x0 x1 plus x0 over there, 1 and 2, plus epsilon squared x1 squared 2x0 x2 plus x1. And that is equal to 0. Okay, and so what do we do now? Sorry, this is 0 plus order epsilon to the third. So what do we do now? And that's really the spirit of perturbation methods. We're going to say that the problem or the governing equation are satisfied at each order independently. Somehow it means that at leading order, which is the name we use to qualify this, at leading order, we will assume that the problem is satisfied. And if you were able to take some sort of magnifying glass and look at what happens at the next order, first correction or second term, you would say, okay, at that scale, the problem is solved, is also balanced. Okay, the governing equations are also satisfied independently at that order. And you do the same again, taking another bigger magnifying glass and looking at other scales. And as you go smaller and smaller and smaller in the scales, what you want to say is that the problem is at each scale, the problem is satisfied. And so the way we write this is to say, okay, at leading order, which means at order 1, or epsilon to the power 0 if you want, the problem is x0 squared minus 1 is equal to 0. At the following order, so epsilon over here, we have 2x0 x1 plus x0 needs to be equal to 0. At the following order, we have x1 squared plus 2x0 x2 plus x1 is equal to 0. Okay, let's just save a little bit of space over here. All right. And then what we do, we solve equations now one by one. At leading order, we end up with x0 squared minus 1 is equal to 0. Leading, in this regular formulation, the leading is always equal to the unperturbed. Okay? And this is because the problem is regular. I'll touch this point a little bit later. Okay, important. That's something you can keep as a take-home message. Okay, so the solution is x0 is equal to plus or minus 1. We know this already. It means we have two roots. Good, that's something we know. Then if you look at the next equation, so at the next order, what do we have? You see that x0 can just factor out because it's not equal to 0. We have just 2x1 plus 1 is equal to 0, which means no matter the value you give to x0, no matter its value, x1 is equal to minus 1/2. And then I saved some space, which was not useful in fact. If we substitute now this into the last equation, we see minus 1/2 squared, this is 1/4. x1 is minus 1/2. So the last equation becomes 2x0 x2 plus 1/4 minus 1/2. This is minus 1/4 that you put on the right hand side. So this is 1/4, meaning that x2 is equal to 1/8 x0, and x0 is equal to plus or minus 1. So it gives plus or minus 1/8. Come back. You got it now? I hope so. You come back to the ansatz. And the solution now is x is plus or minus 1 minus x1, so 1/2 of epsilon, plus or minus epsilon squared over 8 plus terms of order epsilon to the third. And amazing or not, this is the same as what we had before. Look at this. We had plus or minus 1 minus epsilon over 2 plus or minus epsilon squared over 8 plus epsilon to the 4. And we have exactly the same over here. All right. The only difference is the exponent of epsilon squared, meaning that in our case, we were just able to say that the next term in this sequence could be of order epsilon to the third, while from the original problem, we were able to say right away, but that's because we could get its exact solution of the problem and then provide an asymptotic expansion for that. We could say right away that the next term was to the power 4. That's something you could do too with the expansion method, just by keeping an extra term over here, like epsilon to the third multiplied by x3. Proceed with the same derivation here. Write here an equation for at order epsilon to the third, and just realize that x3 is in fact equal to 0, no matter the value of x0. All right, and if you do so, then you get the next term, and in fact, you could keep going as long and as far as you want, and you will recover exactly the same solution. All right, so what is very important to remember here is that we use the expansion method. The expansion method is based on what I'm calling here a regular ansatz. So hoping that the problem is rewritten with the right orders of magnitude, a regular ansatz is something that starts always with the first term that is non-zero, of course, and which should be of order 1. That's how we write. So it should not be small, right? Why? Because if x0 was a small number, so typically same order of magnitude as epsilon, there would be a conflict between x0 and epsilon x1. Okay, because we assume also that x1 is of order 1, and we also assume x2 is of order 1. And we don't want any conflict between two successive terms, because that's precisely what we used in order to say that the problem is satisfied at each order. All right? So this is strictly prohibited. Otherwise, we break the asymptoticness of the sequence. All right, the asymptoticness of the sequence is something that just says that the first term is much larger than the next, which is much larger than the next, which is much larger than the next, and so forth, just to make sure that if we do truncate this sequence, we don't know whether it converges or not, but at least as soon as we decide to truncate this sequence, it provides something that is useful for the engineer and which can be used in order to approximate the solution of the original problem. All right. So we use the regular ansatz. Oops, sorry for that. I'm just trying to summarize. Problem is solved independently at each order. What did we learn from this is that when we have a regular problem, I have not yet defined what regular means, but you will see this very soon in the coming videos. The leading solution is exactly the same as the unperturbed problem, the solution of the unperturbed problem. And that's pretty it by now. All right, so take a rest on this. In the next video, I'll consider again the same problem and try to see whether we can solve it with other approaches. All right, thank you, keep going.